Morning, everyone. Welcome to PNNL's Energy Storage webinar. My name is Wei Wang. I'm the Laboratory Fellow on Grid Energy Storage at PNNL. Today, we have a great pleasure to have one of our scientists, Dr. Emily Saldanha, to give us an introduction on how the machine learning AI is being used for material discovery and system development here at PNNL. A brief introduction to Emily. Emily is a data scientist in the data science and analytical group of the National Security Directorate. Her work focuses on applied machine learning and deep learning for application areas range from energy technologies to computational social science. Her work at PNNL has included the development of interactive machine learning systems, the discovery of causal mechanisms from observational data, and the design of evaluation strategies for social simulations. She currently is the machine learning integration lead for the Energy Storage Materials Initiative, where she develops machine learning methods to improve and accelerate the process of material discovery for energy storage technologies. Prior to joining PNNL in January of 2017, she worked as a data scientist at the Blue Cross Blue Shield Association, where she developed analytical methods for understanding patterns of community health. Emily, floor is yours.
Thanks, Wei. I'm going to go ahead and share my screen to share the slides. All right, hopefully everyone's able to see the slides correctly.
Yeah,
just confirming, great. Emily, it looks great.
All right, thanks. So thanks, Wei, for the introduction, and thanks to everyone for attending today. I'm going to be talking about machine learning methods for material discovery and development for energy storage applications. And just to give a brief overview of the topics I'll cover, I'll start with a introduction to the need for accelerated discovery and design of materials for energy storage, and then talk about some different workflows where machine learning can help with that acceleration, as well as covering some of the ongoing research efforts to address some of the challenges with applying machine learning for these types of domains and applications. So a lot of this work is motivated by the fact that we will need a increasing and growing amount of energy storage capacity to meet the needs of the increased usage of intermittent renewable energy sources in the coming years. And this type of growing demand is really going to bring some significant challenges and require the development of new energy storage materials and systems that will need to be developed and validated beyond currently existing technologies. And redox flow batteries are a promising candidate technology with the potential to address some of these growing grid scale energy storage needs. A redox flow battery functions using liquid electrolytes with dissolved redox active species. And this type of technology has several advantages, including both high safety levels and potential for significantly reduced cost. However, one of the kind of most mature redox flow battery materials, which leverages vanadium as the charge carrier, has undergone quite a bit of development and has reduced the overall cost to the point where the material itself has become the primary cost driver. And so to develop further reductions to meet the targets, there's been increased research efforts into using organic materials as the material for these electrolytes. And this has a number of advantages beyond reaching the cost goals, which is the potential for improved environmental impact, as well as tunability of the downstream battery performance, depending on the characteristics of the material used. and to kind of highlight some of these important design criteria when you're thinking about finding promising materials for these types of batteries. There's a number of key molecular properties that impact the downstream battery performance criteria. So for example, because I'm going to be focusing on it quite a bit in this talk, the solubility is an important driver of the battery's energy density due to its importance in determining the concentration of the redox active species in the electrolyte. And when to look at what the current process for developing effective materials are for these batteries, this is kind of showing an example from some work done at PNNL, which resulted in a Nature Energy publication, where through some extensive testing of these 8 different derivatives of a selected core structure, including both the material characterization as well as the battery level prototyping, they were able to find kind of the best performing and most effective material out of these eight variants on the molecular structure. But this required a lot of trial and error, as well as effort and time-intensive experimental characterization. And the amount of actually known derivatives of this particular core structure is greater than 6,000. And if we expand our view into kind of the full possible space of molecular structures, obviously that's very, very huge and a vast space to explore. So we will definitely need improved and accelerated processes to effectively explore this space and find the types of molecules that can perform well and meet the target battery operation parameters, given kind of all those complex needs and dependencies of the molecular properties. So machine learning methods have a big potential to help with this acceleration. And there's a few different ways they can be employed in the material discovery process. And most of these methods start by leveraging a structure property prediction model, which is able to learn from observed measurements of the target property and the structure of the molecules, kind of the patterns that exist between the structure and the downstream molecular properties. And the model can then take these learned patterns and apply them to new molecular structures to make predictions about their expected values. And once we have models that are able to make these structure property mappings, they can be employed to discover new materials in several ways. First is through high throughput virtual screening methodologies, where we can take large databases of potential molecular structures, predict their properties using our model, and then filter down to the most promising structures to follow up with further testing and validation. One downside of this approach is that you do have to limit yourself to the molecules that exist in the original structural library. So an alternate approach, which enables more flexibility, is what's called an inverse design approach, where we start with our target properties and then use a model that's able to generate novel structures that will hopefully optimize according to those constraints. And this does allow more creativity and more novelty in the structures, but is a little more challenging to train this type of model and develop these methods. And then finally, we can kind of develop a more closed loop workflow involving machine learning if we can, once we make new measurements of molecular properties, kind of feed them back into the training data to further improve the model. And we can use the machine learning methods to actually make recommendations to us about which structure should be measured next. And these can be selected based on either target properties or based on which measurements the model thinks would most improve its own performance. So we can get better and better predictive values using this type of workflow. So there are a number of challenges with applying machine learning in this type of application area that I'll be kind of returning to throughout the talk. One of the primary ones is kind of the limited availability of labeled training data for these models. So the models are reliant on having observed correspondences between structure and properties. And so we need to have measurements of properties for our molecules. And obviously, given the time and effort intensive nature of experimental work, sometimes these data sets can be fairly small with regards to what the machine learning models would really need to learn effective patterns. And kind of a corresponding challenge to this is the challenge of generalizing to new types of molecular structures. So what I'm showing in this plot is basically a 2D representation of molecular structure space for two different data sets, one which does have measured properties and has been used in the past to train solubility prediction models with the orange points, and the blue points being molecules that are randomly sampled from the PubChem database. And we can see that the available training data does not overlap very much with kind of a larger space of molecules. So if we're trying to make predictions in some of these blue regions, we might not expect our models to perform well because the model has never seen a molecule that is like those molecules before during training. And kind of in the other direction to this, where we're trying to generalize, is the task of maybe if we zoom into a very fine-grained region of this molecular space, we can find examples of molecules that are structurally very similar, but those small structural changes do in fact have a significant impact on the resulting molecular property. And this is something that the machine learning models struggle to pick up on. They would view these models as molecules as all very similar and would predict similar values for their resulting property. All right, so the work I'm going to be discussing today was conducted as part of the Energy Storage Materials Initiative. So I just wanted to provide kind of a brief overview of kind of the aims of these efforts. Which is to develop a basically digital twin of a battery system that's able to take both kind of computational representations of a battery, such as machine learning models and simulations, and corresponding physical and experimental systems that are matched with those, so that we can kind of easily model and make predictions about battery performance and operation. And I'll be focusing on kind of the material discovery aspect of this work. So looking at these mappings between structure and properties that will affect the downstream battery performance. But I do just briefly want to highlight that this machine learning work has been conducted in conjunction and collaboration with a lot of other efforts in terms of experimental characterization, simulations, as well as machine learning based modeling of full battery systems. So I will now jump in to some of the machine learning efforts here. And so in order to start training these types of models, we first need to have collected a data set to support learning the structure property relationships. And this is showing the solubility based data that we have aggregated from a number of different databases and sources to create a data set of about 22,000 molecules with corresponding solubility values. And a couple of things to note here is that this data set is kind of significantly larger than previously existing data sets, more example molecules to learn from, as well as more diverse in terms of the molecular properties. So just as an example, the molecular mass, we span a greater range in our molecules than some of the other data sets that were previously available. And I'll talk later about how the size and diversity can really impact the downstream modeling performance. Another thing to keep in mind is that the solubility prediction can be pretty challenging for a number of reasons, but one of which is that it does span kind of such a large range. And in this data set, we actually have molecules kind of spanning about 12 orders of magnitude in the main part of the distribution here. So we actually usually operate on predicting log solubilities, so predicting kind of the overall order of magnitude within this very broad range of values. So once we have a data set to train, we need to first be able to represent those molecular structures in a way that the models can understand them. So we need to develop basically numerical representations that encode that molecular structure. And we've looked at kind of 4 different possible representations, one of which relies on computing molecular and quantum descriptors to describe the structure. So this can include simple things like just the size of the molecule, the number of rings, things like that, as well as much more complex kind of constructs derived from the structure. But one of the downsides there is that that kind of limits the information available to the model to those factors that we pre-compute. And so it may be beneficial for the models to have access to the raw structure to learn patterns that we may not have thought to pre-compute. So we looked at 3 different kind of raw structural representations for modeling, including graph-based representations of the molecule, string representations using the SMILE string, and 3D coordinates of the atoms in the molecule. And these are all trained on machine learning models, which are basically designed to match and process this type of information. These are all kind of deep learning based architectures. So when we train these models on our data set, we achieve about a 1 order of magnitude level of error. And this is showing the predicted values versus the actual values for the 4 different model types. And what we find is that the best performance is actually achieved by the molecular descriptor based model, here the blue one, which shows that actually there is a benefit to pre-computing these features to describe the structure, and the model is more easily able to learn if you can provide that more processed level of information. However, we do find that our best performing raw structural model, the graph-based model, almost equals the performance of the molecular descriptor model. And we also find that there is a high level of correlation in both the predicted values and the errors of the predictions between our 4 different models, kind of showing that these models, despite the differences in how the structure is represented, are able to learn similar structure to property mappings in the end. So they are flexible to that representation. So once we've developed a predictive structure property model, this slide is kind of illustrating the benefit of that in terms of applying it to high throughput virtual screening workflows. So as an example, if we take a kind of random sample of PubChem molecules and use our 2 best performing models, the molecular descriptor model and the graph-based model, to predict the solubility, we find that we can very quickly process this large number of molecules using our graph-based model, although it is a little slower for the molecular descriptor model because some of these predefined features are time intensive to compute. And what we can see if we look at the predicted solubilities is that overall this kind of random sample of structures does have lower solubility than our PNNL collected data set, which is more targeted towards achieving this kind of high level of solubility that is beneficial for the battery performance. We do find that in this large set of molecules, there is a small tail here getting up to high values. And if we kind of extrapolate how many we see here to kind of the full set of possible structures in PubChem, in the end, that does lead to a large number of potential molecules with high solubility according to the model. So that's kind of where the benefit of these models come in, is that we quickly process through these large libraries to find promising candidates. So next, I will discuss kind of some of the challenges with machine learning that I mentioned earlier, and one of which being kind of the data sensitivity of the machine learning model performance. So models will perform better when they have larger training data sets. And we took a look at this within our data set by kind of sampling out smaller and smaller data sets to train our model and see how much that reduced performance. And what we find is that error is reduced by about 0.06 orders of magnitude whenever we double our data size. So that's good. Collecting more data can improve performance. However, we do want to note that there can be a bit of a diminishing returns there, and that now we have 20,000 molecules and we have to double again to 40,000 to get a further level of that reduction. So that does become, of course, challenging with the amount of effort it takes to obtain those measurements. We also identified that not only the overall performance, but also the performance in certain subsets of molecules, so such as certain solubility ranges, is dependent on the availability of data. So we achieved the best performance in our model for the log solubility range between -4 and -2, in the region where we have kind of the most available training examples. So next, I'm going to talk about some kind of potential solutions to addressing kind of these data limitations. And the first is around actually data collection. So how can we obtain kind of more data points for our models to train on beyond kind of the experimental efforts. And one is making sure that kind of existing measurements that are published in the literature are able to be incorporated into the database. And so to that end, we've been developing natural language processing methods to extract molecular property data from scientific papers. And these methods are based on an NLP technique called named entity recognition, which is more typically applied to do things like detect people, places, and things like that from within text data. And they work by basically splitting the text into words and training a classification model that can detect which of these types, if any, that word corresponds to. And so we'd like to develop a customized method that doesn't do these general types, but does more specific chemically related entity types, such as the chemical name, the solubility value, the solubility unit, and maybe some contextual information. So in order to train these types of models, we do need to, again, have some amount of labeled data. So we need example sentences where we've tagged these types of words that we want to extract automatically. So to do this, we use some large available publication databases, found promising sentences, and use kind of some automated methods to tag them. So in the cases where the information is expressed in a very straightforward and common way, we were able to use kind of existing regular expression methods to tag those, and then also did some manual tagging to capture kind of the more complex phrasings that you need a human to look at and understand. And after training on this data set, we find that we do get reasonable performance at automatically tagging these types of words that contain the solubility property measurement information. And we have integrated this tagging capability into basically a pipeline that can monitor some APIs for new publications, identify promising papers, tag those sentences using our NER model, and then of course we don't want this to be kind of yet fully automated because the model does make some errors. So final checks before adding kind of those new measurements into the database. All right, but as I mentioned, adding in new data points, right, does have kind of some diminishing returns in terms of applying just the straightforward structure property training methodology. So what are some ways we can get around kind of this limitation of just the total number of labeled data points may be low, and further improve the models. So one way is by pre-training using large data sets that may not have kind of the value you're trying to predict, like solubility, but may have some other types of labels that still enable the model to learn some chemistry knowledge. So for example, there are these QM9 and PC9 data sets, which have about 100,000 molecules in them and some DFT computed labels of various properties. And if we train a predictive model on this task first, and then start the model from what it learned from this training as the starting point for training on the solubility task, that can be helpful. And what we find if we look at the learning curves for these models, which is basically how the performance is improving as we show the model more training examples, that we don't see much of improvements of using pre-training on the molecular descriptor model, but we do see a boost, kind of the red with no pre-training to the blue and the green with pre-training on the graph-based model. And that shows that learning kind of the more complex patterns from raw molecular structure to resulting property does benefit from this pre-learned kind of chemistry knowledge. The types of structural patterns it learns for the first task transfer to the second task and help it learn faster and achieve a better performance. But again, that does rely on having these labeled data sets on the pre-training tasks. And there's obviously much more available unlabeled data out there regarding molecular structures. So these are just these large libraries of molecular structures that exist. For example, the PubChem and Zinc databases that have 100 to 200 million data points in them. And so if we were able to use those to incorporate some prior chemical knowledge into our models, that would be really beneficial to get some information from that big diversity of molecular structures. And there's a number of different methods actually for doing what's called unsupervised or self-supervised training, where we don't need to have access to any property labels. So one example is an autoencoder, where we put the molecular structure as the input to the model and also ask the model to reconstruct that structure at the output, where kind of the catch there is that there's a limited capacity in the middle of this model. So it has to compress the information about the structure into a low dimensional vector representation before doing the reconstruction. Other approaches include things like masking out knowledge that the model has about part of the molecular structure and asking it to fill it back in again. So it has to learn something about chemistry in order to accomplish that infilling task. And then another model developed recently was related to kind of converting between different representations of the structure. So in this case, taking a SMILE string and converting it into an IUPAC string. And the model does have to learn some chemistry and conventions of the naming to do that. So if we do these types of pre-training tasks, what we find on some fairly large pre-training data sets, what we find is that some of these methods are more helpful than others. And in particular, we see that the model errors are reduced compared to training from scratch if we do some of these string-based pre-training methods, including the translation or a string-based masking approach. But that ultimately we get kind of the best performance and are able to improve actually upon our previous best model if we do a graph-based masking pre-training approach. So that seems to be the most effective for incorporating some relevant chemistry knowledge into the model to then fine-tune on the solubility prediction task. And so we were kind of interested in what does this pre-training actually teach the models about in terms of chemistry knowledge, and how does that help the downstream property prediction performance? So one thing we're looking at here is whether the basically if we look at the vector representation of each molecule that is learned by these pre-training approaches, so which molecules does the model think are similar after doing this pre-training approach? We can look at that kind of 2D projection of the chemical space as viewed by the pre-trained model and look at how it's organized with respect to some molecular properties. So for example, we find that the string-based masking pre-training approach does tend to organize the molecular space according to some of these properties. So there seems to be a gradient here in terms of the molecular weight. And that larger molecules are placed near each other according to the model, and that smaller molecules are placed near each other. Interestingly, we don't see the same pattern for the graph-based masking pre-training model. It does seem a little bit more scattered and random here in terms of the properties and the kind of layout of this space. But this is, of course, the model that did prove to be the most useful for the downstream task. So that's kind of interesting. And one thing we were able to kind of maybe trace this back to is kind of the distinction between how the models are arranging the molecules in terms of their similarity, in terms of what we're referring to as global knowledge versus local knowledge. Like a model which arranges the molecules in a global way would introduce this type of overall gradient in the space, whereas one that organizes them in a local way would tend to put similar molecules close together in a cluster, but not necessarily arrange the clusters in any kind of globally varying configuration. And what we find is that pre-training methods, which do encode chemical knowledge in a kind of a more local way through these clusters, do in fact lead to better final performance on the downstream task. So that shows something about the way these models might be reasoning about the kind of properties of the molecules in terms of their similarity to other molecules within the space. So next I'll jump to another challenge that I mentioned, which is this aspect of generalizability of the models. So how do we know kind of where we expect the models to perform well and where we expect they might not perform as well because we're asking them to tackle some kind of structure that they haven't seen before or had enough information about during training. So here we looked at basically finding within our data set the molecules that seem to perform poorly in terms of their predictive error. So those molecules which either had high error, or if we retrain the model many times to get some variability, molecules which have a large amount of variation in their predictive error. So these are molecules which are not able to be predicted as well by the model or as consistently. And what we can then do is look in our molecular descriptor feature space to identify the types of structural features which are more common amongst these outlier molecules than they are amongst the non-outliers, which are predicted well. And we can apply thresholds then in our descriptor space to kind of separate out kind of the core set of molecules that we expect the model to perform well on, and also quantify how well we expect it to perform by measuring error on these filtered, increasingly filtered data sets, coming down to kind of the core set that we can consider to be where the model should apply well. And this gets back to the point that I mentioned earlier about kind of the impact of data size and diversity on model performance. So not only does a larger, more diverse data set maybe give you better overall performance, but it also kind of increases the range of molecules that you can successfully apply the model to. And what these plots are showing is, again, a kind of 2D projection of molecular space, where I've marked molecules which kind of are outside the applicability domain of the trained model in red, and molecules for which we can estimate the model performance in the color scale. On the left for a small training data set, and on the right for our large training data set. And the first thing we can see is that there's a kind of significant region of the molecular space to which we can't expect the model trained on the smaller data set to generalize well, because it's never seen molecules like that before during training. And that also we see that, amongst this region of space, that we do see kind of some regions which are more challenging, higher error, and some regions which are less challenging, lower error. But that the overall level of error on the larger data set is overall lower. We're doing better overall, and that we can cover more space. Basically, all of the space that we can see as far as the sample of molecules. So that size and diversity of the data set is definitely improving the usability of these models. So that brings me to kind of one of the other workflows that I mentioned at the beginning, in terms of, given that we do have some limits to the generalizability of our models, some regions where it may not apply well, how can we kind of accelerate the ability to generalize to these regions by collecting new data points and adding them into the training data sets? So this is that experimental design workflow, where we want to make the best use of our limited experimental resources to optimize the selection of these molecules. In the machine learning implementation, this is also referred to as an active learning method, where we want to select new data points to label in a smart way. And there's several different possible criteria for doing this selection of the new data points. We could try to optimize the property, find promising candidates, or we could try to improve the performance of the model, or help it generalize faster. So in our case, we were looking at uncertainty-based sampling. So we'd like to sample new molecules to add to the data set based on those that have the highest uncertainty. And these should be molecules that are probably more outside the current applicability domain of the model, and kind of help the model adapt to new region where it's most uncertain by focusing on those data points. So in order to do this, we first need to augment our machine learning models with uncertainty quantification capabilities. So kind of by default, these deep learning based models will just output kind of a fixed value for the most likely solubility or property value. And we'd like to now get a kind of sense of the possible distribution with the uncertainty. And there's a number of different methods you can use to do this. And in the interest of time, I won't go into too much detail. But you can see that if we add in these uncertainty quantification methods, now we can get a sense of both the actual prediction of the model as well as how that kind of uncertainty correlates with the errors that we're seeing in the predictions. So if we kind of use those uncertainty values now to we start from a small training set, use the uncertainty values to select which new data points to add into the training set and train the model again. We would like to see that by using this smart sampling approach, we can do better than just randomly sampling new molecules. And specifically, we'd like to see that we can do better at generalizing. So if I use my uncertainty-based sampling, I should preferentially select more molecules from these out-of-domain regions than if I just randomly sample from the full data set. And so what we find is that, in fact, we do get further reductions in error on those out-of-distribution molecules if we do this active learning-based sampling, but the effect is still fairly small. So less than 0.5% for most of these uncertainty methods. And we would like to improve our performance on our out-of-distribution molecules while not reducing our performance on our in-distribution. We would like to maintain that existing knowledge. So we can see for these uncertainty methods that is the case. If we kind of cheat and actively use our known knowledge of the out-of-domain regions to only select those, we do see a much bigger boost in performance at some cost to the in-distribution performance. But this does give us kind of an upper bound of what we can expect beyond random sampling. So the upper limit here on improvement beyond random sampling is reasonably small. With the current methods. So this is definitely an area for future research where we'd like to really reduce these data requirements that we need to generalize to these new regions of molecular space. So I'm going to jump now to another one of the challenges that I mentioned at the beginning, which is this challenge of predicting the impact of fine-grained structural changes to the molecule. And what we've found here is basically that when we have these very similar structures that may actually have significant differences in their target property, the models do tend to view these all as nearly identical and make very similar predictions. And the way we kind of probe this is by measuring whether the predicted values of solubility for example, the set of isomer molecules in our data set are ranked in the same order as the actual values. So if the models are correctly able to infer which of these small variants has the highest solubility and which has the lowest, then this would have a high ranking correlation value. And we find that, if we take random groups of molecules, so just randomly sample, for example, 3 molecules, the models perform very well at ranking those in order. And almost as well as that if we take a set of molecules which all have the same core structure, but potentially different functional groups. So that is not too much more challenging for the model. But what becomes really challenging is if we have these isomer structures, so very fine-grained variants on the structure are very, very difficult for the model. And this, may partially be because these groups of molecules actually do have less solubility variation than random groups. But if we do control for that and say, given the solubility difference amongst this group of molecules, how well do I rank them? And even when the isomer groups have significant differences, we do see much reduced performance compared to random groups of molecules. So we've tried a number of different kind of modeling and data representation approaches to try to address this, but it does prove to be kind of very challenging when using data-driven models to kind of understand these fine-grained differences, because it does look very, very minor to the model representation. So I just want to highlight kind of one direction we're currently working to address this challenge is kind of incorporating more chemical knowledge into the models. So all the models I've discussed so far have been purely data-driven, just given observed patterns between structure and property. The model wants to learn those to predict the property. But obviously we do know some things about the processes of solvation and the underlying kind of thermodynamic cycle that drives the solubility values. So if we can constrain the models to incorporate some of that knowledge, such as by first predicting some of the underlying factors of the sublimation and hydration processes, and computing the solubility from those known factors, I think this should help the model kind of develop a better understanding of the actual mechanisms behind the resulting values. And then finally, I'd like to just touch on the last workflow that I discussed at the beginning, which is the inverse design workflow. And we're just starting some preliminary work in this area. So I will mainly kind of outline the concept behind this. And again, here we're trying to ask the model to generate new structures based kind of on the target properties we'd like to achieve. And so kind of one first step in this process is maybe just kind of unconstrained molecular generation. Can we generate new molecular structures that resemble in some way some distribution of molecular structures that we had in our training data? So for example, if we have a chemical space with this distribution in the training set, can we then generate new molecules that were not in the training set, but that are structurally similar to those? And then we'd like to augment that with molecular generation for target proper functionality. So if we take the same molecular structure space and look at how the solubility varies in the space, we can see we have higher solubilities in this region of the space. And so we'd like to preferentially generate new molecular structures from this region of the molecular space. So there's a couple components that you do need for this inverse design process. The first is some capability to actually generate these structures. So the model needs to have a pipeline for that. So a couple ways it can be done includes kind of an atom-based generation of structure. So given a starting structure or from scratch, add atoms individually into the structure until the model views it as complete. This can also be done at kind of the fragment level. So adding whole fragments at a time to the molecule. And then there's been some recent work on actually generating molecular structures using kind of the reaction tree. So thinking more about actually the underlying synthesis and generation processes for the molecules. And once you have a method for asking the model to produce a molecular structure, we then need to have a way to optimize the target properties. So generate me structures that are likely to have the properties that I'd like. And there are a couple methods for that. One is reinforcement learning, where basically the model starts constructing these molecules. They're passed into our structure property prediction model to generate a reward function, and the model is encouraged to take actions in this generation space that lead to higher levels of that reward. So more closely towards the target values of the property. Another method is kind of Bayesian optimization, where if we have a latent space, a representation of the molecular structure and a model that can make a prediction about the property from that latent space, we can kind of move around in this space to find regions that are likely to have the kind of property that we would desire. And then finally, we can, do what I mentioned in the last slide is the unconstrained generation, but where our training set for the model are molecules that have kind of the target property. So if I have a set of molecules that are near my target property, can I generate new molecules that are similar to this set? And just to kind of quickly illustrate one method for inverse design that is based on, this is the mole DQN method that uses reinforcement learning to kind of modify an existing structure. And if we use our solubility prediction model as the reward function for this method, what we see is that we start with our core structure. We are in fact able to generate molecules with increased solubility, although again, maybe not as high as we would like. So further development is needed to kind of push this improvement even further. But if we look at the kind of molecules that it's generating, we can also see some other issues here that, optimizing for a single property at once is not likely to lead to kind of optimal performance as far as practical applications, right? Because there's going to be a lot of synthesis and complexity issues arising if we just kind of let the models make any modifications to optimize this single property. So definitely there's future work to be done to kind of address some of those issues in effective inverse design. And with that, I'd like to wrap up and just kind of highlight the kind of potential of these methods to really accelerate the ability to discover new materials, to increase the performance of the battery systems, and that current research work is ongoing to address a lot of these challenges that I mentioned. And I'd also just like to kind of thank and highlight all the collaborators and research team that I worked with on this, and the broader Energy Storage Materials Initiative team, which is shown here. And with that, I will be happy to take questions.
Thank you, Emily, for this very informative talk. We do have some questions from the audience. The first one is regarding machine learning workflows, where one of the outputs is suggesting as to which molecular structure to test next. Could you elaborate more on this point? Specifically, is it any low-vol structure that it proposes?
What was the last part of the question?
Last part is what is it any of the low-vol structures that the model will propose?
So yeah, the structures that it will propose will kind of depend on what criteria you would like to optimize for. So one thing is if you're trying to find the best performing molecule, you can use the predicted property values to say these ones are the most promising to achieve those target values. If your goal is to make the model perform better, you can look at basically which molecule predictions are the most uncertain. And so those are the ones you might probably want to add to the data set again, so that the model can improve its own performance on those molecules. So kind of the selection criteria will be based on what you're trying to achieve there. And again, this is you're kind of limited into which molecules you're making predictions for there. So you have some structure library, and you're like, which of these possible structures should I measure next? So you kind of get the predictions and associated uncertainties and things like that for that library, and see among these which ones would be best suited to achieve that objective.
Okay. The next question is to help reach net zero goals, gigawatt or terawatt of energy from utilities or renewable sources are needed for the organic redox flow batteries deployment, and hence huge volume of electrolytes are needed, no matter how optimal the organic molecule is. The question is, are you considering dimensional design of storage facilities needed to store electrolyte? Will you consider underground storage of electrolytes due to the high volume of them?
Yeah, so I think that's coming in, that question's getting at kind of there's other factors, right, beyond just does this molecule, for example, we have focused in these efforts a lot on the solubility, which is just one factor that impacts the battery performance. And so there's a lot of other factors to consider, and beyond battery performance, one of those might be the actual feasibility of this material. So synthesizability, kind of ability to obtain the input materials and things like that. Yeah, definitely looking at those other dimensions would be important in the final selection.
Yeah, I want to add a little bit on that. So the future energy storage system most likely will be at least substantial part of it will be distributed system, right? So we have a huge amount of energy, but there will be in distributed system. So I think regarding the volume question, it's very important to understand that the volume is decided by the energy density of the, in our case, for the redox flow batteries, by the energy density of electrolyte. So, so for example, that Emily's work is to primarily right now, one focus is to increase the solubility of the organic molecules, which directly increase the energy density, and that reduce the volume. The current best performance level, the organic systems already reach over 4 molar of the electron concentration, already double double, even tripled more than doubled the energy density of the vanadium flow batteries. So there's a great hope that we can identify new organic molecules that even have a higher energy density, and that's a smaller volume. Right. The other question is, do sterile isomers cause a variable solubility within compounds that have the same chemical formula? If so, is there a way to account for that with the machine learning model and the training data? I think you have lots of experience with that.
Yeah. So that's, yeah. I think it can affect the resulting properties, and that's definitely a challenge, and needs to be one. Well, the first step is just making sure that the molecular representation can incorporate that information. So if we're using a representation that doesn't use 3D information, for example, it won't even be able to tell the difference between those two molecules, right? So first, we need to make sure we have a representation that does understand that these two molecules are different. And once that's the case, needs to understand that this difference actually matters for the solubility. And we do see if we augment our graph-based models with 3D information, an improvement in the isomer ranking performance, but still not to very high levels. So it's kind of that second step that still seems to be a challenge for the models, that it doesn't understand that this fine-grained difference, this small structural variation, does in fact lead to a downstream solubility difference. And that, I think, is partially due to the fact that we're asking it to make predictions across a diverse range of molecules, and so it looks at this pair of very different molecules and understands that they're very different and have a solubility difference. And in comparison, these two very similar molecules it thinks are not that different, so it should have a similar predicted solubility. So even if it does have access to kind of the structural difference there, the current methods are not yet kind of understanding the potential impact of that.
Okay. The next question is, to train your model and extract public databases, do you differentiate the solubility of free acid or base with their salt?
So the current database is, I think, not differentiating that. So kind of collecting just a wide range of solubility values from the existing databases under, I think, like just neutral pure water conditions.
Okay. So Emily, I want to ask you a question. The current research, your research is mostly focused on the properties that are important for the redox flow batteries. For our audience that working in other areas, is this method easy to transfer to be used for other energy storage chemistry systems?
Mm-hmm. Yeah, so in principle, the same methods can be applied to other target properties. Given enough data with the corresponding kind of material configuration information and the resulting property, these can be applied to other target tasks. Or kind of the catch there is the need to have enough available training data to learn those structure to property mappings. And that's where they kind of think starting from scratch for every new property prediction task is quite intensive in terms of the required kind of experimental data collection efforts. And so I think the extent to which we can develop pre-training methods and other approaches to make more effective use of smaller amounts of data will really kind of help in the transfer of these things to new application areas. So some of that chemical or materials knowledge can be pre-learned by the model. The amount of data needed to be collected for a new effort will not be as extensive. But in principle, the basic techniques are the same, just in terms of taking the new data set with a different property and kind of plugging it into the model training procedure would be not need any variation, because they are kind of, as I mentioned, purely data driven. So if you are looking to add kind of some specific chemical knowledge around the property, then it would vary property by property. But in the purely data driven methods, it does transfer fairly easily.
Okay. Do we have any other question from the audience?
Wait, I don't think we have any other questions.
We have a new question?
No, there's no other questions.
No other question. Okay. Well, thank you, Emily, for giving us a wonderful talk, and thanks everyone for joining our webinar. I want to encourage you to come back to visit this seminar series. On the screen, there are some upcoming webinars. So on the October 6th, there's an energy cost and performance assessment and database. If you want to use machine learning data, you got to have the database first. So hope everyone can join us next time on the October 6th seminar. All right. With that, we'll wrap up this webinar, and thank you everyone, and hope you have a great day.